There is a place in the cosmos where the laws of physics as we understand them reach their limit. Not a place where things become difficult to calculate, not a place where our instruments fail. A place where the very fabric of space and time, the architecture of reality itself, bends so severely that our best theories whisper something extraordinary and then go quiet. This place is called a black hole. And today, I want to ask you a question that has occupied the minds of physicists, mathematicians, and philosophers for more than a century. A question so strange that the answer, when you sit with it long enough, will alter how you think about time, about existence, and about what it means to be anywhere at all. What actually happens to you if you fall into one? Not what happens to your spacecraft, not what a distant observer watching through a telescope might see. What happens to you, your body, your consciousness, your experience of time as you cross the boundary of a black hole and move toward its center? The answer is not what most people expect. In fact, the answer contains within it a contradiction so deep that it sits unresolved at the frontier of modern physics. Two of our most successful theories, general relativity and quantum mechanics, each give a different answer, and both, as far as we can tell, may be right. That is not a failure of science. That is an invitation to the edge of what we know. Let us begin. You might be tempted to think of this as an exotic thought experiment, something reserved for science fiction films, for the speculation of armchair astronomers. After all, you are unlikely to fall into a black hole. The nearest known stellar mass black hole is perhaps 1,000 light-years away. The supermassive one at the center of our galaxy, Sagittarius A star, is 26,000 light-years distant. But that is precisely the wrong way to think about this question, because what happens when something falls into a black hole is not merely a story about falling. It is a story about the nature of space. It is a story about the nature of time. It is a story about whether information, the fundamental description of what something is, can be destroyed. And that last question has consequences not just for black holes, but for the entire logical structure of the universe. If information can be destroyed, then the universe is not, at its deepest level, a deterministic system. The past cannot be recovered from the present. The future cannot be predicted from the past. Cause and effect, the very backbone of science, becomes uncertain in a way that is not merely practical, but fundamental. This is called the black hole information paradox, and it remains one of the most important unsolved problems in theoretical physics today. So when we ask what happens when you fall into a black hole, we are not indulging in fantasy. We are probing the deepest structure of reality. We are asking whether the universe, at its core, makes sense. That is why this matters. Let us start at the beginning, not with equations, but with an image. Imagine space as a vast three-dimensional fabric. Not a flat sheet, that is a useful simplification, but something more like the air itself, filling all of existence in every direction. Now imagine placing a massive object inside that fabric. The sun, for instance. Its mass causes the surrounding space to curve slightly. Planets orbit the sun not because they are being pulled by an invisible force in the Newtonian sense, but because they are following the straightest possible path through curved space. This was Einstein's great insight. Gravity is not a force. Gravity is geometry. Now compress the sun. Compress it further. Compress it until all of its mass, all of it, is packed into a sphere about 3 kilometers across. At that density, the curvature of space around it becomes extreme, so extreme that not even light, moving at 300,000 kilometers per second, can escape from within a certain radius. That radius defines the event horizon. It is not a physical surface. There is no wall, no membrane, no visible boundary. It is simply the point of no return, the radius within which the escape velocity exceeds the speed of light, which means nothing, no matter, no information, no signal of any kind can travel back out. From the outside, a black hole appears as a region of absolute darkness. Around it, space-time is so distorted that light from behind a black hole bends around it.
This is why, when astronomers captured the first image of a black hole, the supermassive black hole at the center of the galaxy M87, published in 2019, they saw not darkness alone, but a bright ring of glowing gas bent into a circle by the immense curvature. The darkness in the center is the shadow of the event horizon itself. This is real. This is not theoretical. We have seen it.
Now we come to the heart of the question. And to understand it, we need to introduce something that Einstein understood deeply: the relativity of time. Time does not flow at the same rate everywhere. This is not a philosophical claim. It is an experimentally verified fact. Clocks on GPS satellites, which orbit higher in Earth's gravitational field, tick measurably faster than clocks on the surface. The difference is small, microseconds per day, but it is real, and if we did not correct for it, our GPS systems would accumulate errors of kilometers within hours. Gravity slows time. The deeper you are in a gravitational field, the slower your clock ticks relative to someone outside that field. This effect becomes more extreme as gravity intensifies, and near a black hole, it becomes almost incomprehensible. So let us construct our thought experiment. We have two observers. The first, let us call her the distant observer, is watching from far away, safe from the black hole's influence, floating in a spacecraft that maintains a fixed position. She has a powerful telescope aimed at the event horizon. The second, let us call him the falling observer, has decided, for reasons we will accept without questioning, to fall freely into the black hole. He is in a pressurized spacecraft, in good health, and he is falling feet first. From the distant observer's perspective, something deeply strange happens. As the falling observer descends toward the event horizon, the light he emits, every photon he sends outward, must climb against increasingly severe space-time curvature to reach her telescope. This requires energy. And as light expends energy climbing out of a gravitational well, it loses frequency. It redshifts. Visible light becomes infrared. Infrared becomes microwave. Microwave becomes radio. Simultaneously, the rate at which she receives those photons slows. The falling observer is moving through a region of increasingly slowed time relative to her. His clock, from her perspective, is ticking slower and slower. The images she receives are spaced further and further apart. The result is this. From her perspective, the falling observer never crosses the event horizon. He approaches it asymptotically. He slows, he dims, he redshifts into invisibility. But in principle, in the mathematics, he never quite reaches the boundary. He is frozen there in her perception for eternity. Or rather, he fades to nothing, since the light he emits becomes too redshifted and too infrequent to detect. This is not an illusion. Within her reference frame, within her experience of time, this is what genuinely happens. He is, from her perspective, suspended at the edge of forever. Now let us ride along with the falling observer himself. Here is where the counterintuitive truth of general relativity reveals itself with full force. From his perspective, nothing special happens when he crosses the event horizon. Read that again. Nothing special. No alarm sounds, no physical sensation marks the crossing, no barrier is encountered. If the black hole is massive enough, and supermassive black holes at the centers of galaxies are millions to billions of times more massive than the Sun, then the curvature of space at the horizon, while absolute in terms, is gentle enough that a human body would not be disrupted at the moment of crossing. He simply falls. Freely, as if in weightlessness. The event horizon passes him, or rather he passes through it, without ceremony. And yet, something fundamental has changed. Every path through space-time that was previously available to him, every direction he could have traveled, has been altered. The singularity at the center of the black hole is no longer a place in space, it is a place in time. It is his future, and in the universe as we know it, you cannot avoid your future. He will reach the center. The mathematics are unambiguous about this. The only question is what he encounters along the way. As he falls deeper past the event horizon toward the center, he begins to experience what physicists call tidal forces. Imagine standing on the surface of the Earth. The ground pulls you downward. Your feet are slightly closer to the center of the Earth than your head, so gravity pulls your feet very slightly more strongly than your head. On Earth, this difference is so small you cannot feel it. Near a stellar mass black hole, the difference in gravitational pull between your feet and your head becomes enormous. The force pulling your feet is dramatically stronger than the force pulling your head. Your body is stretched, vertically elongated, and horizontally compressed. This process, described with characteristic scientific precision and unexpected poetry, is called spaghettification. For smaller black holes, those a few times the mass of the Sun, this tidal disruption would begin well before reaching the event horizon. You would not survive the approach. But for a supermassive black hole, 1 millions to billions of times more massive than the Sun, the curvature of space at the horizon is so far from the central singularity that tidal forces at the event horizon are relatively modest. You would cross the horizon intact. The fatal stretching would come later as you approached the singularity. The time between crossing the horizon and reaching the singularity, your remaining lifetime inside the black hole, depends on the black hole's mass. For a stellar mass black hole, it might be microseconds. For a supermassive black hole, billions of times the mass of the Sun, it could be hours. Those hours would be spent in a region of the universe that no signal has ever left, a region from which no information has ever escaped to tell us what is there.
For most of the 20th century, the story I have told you was considered essentially complete. The distant observer sees the falling observer freeze and fade. The falling observer crosses the horizon peacefully. Both descriptions are consistent. The apparent contradiction between them is explained by the relativity of simultaneity. Different observers in different reference frames simply have different valid experiences of time. This is the beauty of general relativity. It is internally consistent. It is elegant. It works. But quantum mechanics introduces a complication that refuses to be dismissed. Quantum mechanics tells us with equal certainty and equal experimental verification that information cannot be destroyed. Every physical process at the quantum level is reversible in principle. If you know the complete quantum state of a system at one moment, you can, in principle, reconstruct what it was at any earlier moment. The past is encoded in the present. Information is conserved. Now consider Hawking radiation. In 1974, Stephen Hawking made one of the most remarkable theoretical discoveries of the 20th century. By applying quantum mechanics to the region just outside a black hole's event horizon, he showed that black holes are not completely black. They emit a faint thermal radiation, now called Hawking radiation, caused by quantum effects near the horizon. And as they emit this radiation, they slowly lose mass. Over an extraordinarily long time, for a stellar mass black hole, longer than the current age of the universe by many orders of magnitude, a black hole will evaporate completely. This creates a crisis. If information cannot be destroyed, then the information about everything that ever fell into the black hole must somehow be encoded in the Hawking radiation that escapes. The radiation must not be purely random thermal noise. It must carry in subtle quantum correlations the complete record of everything the black hole ever consumed. But how? The event horizon, by definition, is the boundary from which nothing escapes. The Hawking radiation is generated outside the horizon in empty space through quantum fluctuations. How could it possibly carry information about what happened inside? In 2012, a group of physicists, Ahmed Almiri, Donald Marolf, Joseph Polchinski, and James Sully, whose work is now referred to as AMPS, published a paper that brought this crisis to a head. They showed that the two requirements, peaceful crossing of the event horizon and information conservation through Hawking radiation, cannot both be true simultaneously. If Hawking radiation carries information, then the quantum entanglement structure near the horizon must be so disrupted that the event horizon is not a peaceful, empty region of space. Instead, it would be surrounded by an intense wall of high-energy radiation, a firewall. Any infalling observer would be incinerated the instant they crossed the horizon, not hours or microseconds later at the singularity. The peaceful crossing that general relativity predicts would be wrong.
But if general relativity is right, if the horizon is peaceful, then information must be destroyed and quantum mechanics is wrong. Both cannot be right. And yet, both are supported by overwhelming experimental evidence. This is the Firewall Paradox. It remains unresolved. It is not a mathematical curiosity at the edge of physics. It is a direct confrontation between our two most successful theories of nature, using a thought experiment at the simplest possible scale, a single observer falling into a black hole. The resolution, when it comes, and physicists are confident it will come, will require a new framework, something beyond both general relativity and quantum mechanics as we currently understand them, something we do not yet have.
The singularity at the center of a black hole is not, in the current understanding of general relativity, a place. It is more accurate to say it is a breakdown of the theory. It is the point at which the mathematics produces infinities, curvatures that become infinite, densities that become infinite, time that effectively ends. This is widely understood to mean that general relativity is not the final word. Near the event horizon, quantum effects at the smallest scales, the Planck scale, must become dominant. A theory of quantum gravity is needed to describe what happens there. We do not have a complete, verified theory of quantum gravity. String theory is a candidate. Loop quantum gravity is another. The holographic principle, developed in part through the work of Juan Maldacena, suggests something even stranger, that the physics inside a black hole may be entirely equivalent to, fully encoded in, physics on its two-dimensional surface. This is the holographic principle, and if it is correct, then the three-dimensional interior of a black hole is, in some deep sense, not more real than its two-dimensional boundary. Which raises a question that extends far beyond black holes. What if the same is true of the universe itself? What if the three-dimensional reality we inhabit is a kind of projection from a two-dimensional surface at the boundary of the observable universe? This is not established fact. It is a serious theoretical framework being actively explored by some of the finest physicists in the world. I mention it not to disorient, but to illustrate how far a single question, what happens when you fall into a black hole, can reach into the foundations of everything. We tend to think of time as universal, as a river flowing at the same rate for everyone, everywhere. Tuesday follows Monday, tomorrow comes after today. The universe ages, and we age with it, all at the same steady pace. But time is not like this. It never was. Einstein showed us, more than a century ago, that time is local, personal. It flows at a rate determined by gravity and velocity. Two people can start at the same moment and, after different journeys through space and gravity, arrive at the same place, having aged differently. This has been confirmed in laboratories, in particle accelerators, in the GPS satellites we rely on every day. A black hole takes this truth and amplifies it to its extreme. Near the event horizon, time slows to nearly nothing from the perspective of someone watching from far away. An observer far from the black hole could, in principle, watch 1 billion years of cosmic history pass while someone near the horizon experienced only hours. Time is not a constant. It is a dimension of space-time, shaped by the matter and energy within it. The universe does not have a single clock. It has as many clocks as it has positions in space, and no two of them keep perfectly identical time. This should give us pause. The certainty we feel about time, about past, present, and future as fixed, universal categories, is a local illusion, valid within our immediate experience, but not written into the fabric of the cosmos. There is something deeply personal about the information paradox. Everything about you, every memory, every configuration of neurons, every learned pattern of thought and feeling is information. It is the particular arrangement of matter and energy that makes you, you, and not someone else. If information can be destroyed, then what enters a black hole and is lost to Hawking radiation, scattered into thermal noise with no recoverable structure, is gone. Not just the matter, the pattern, the arrangement, the record of what it was. If information cannot be destroyed, then everything that has ever fallen into a black hole still exists in some encoded form in the radiation that slowly leaks out. The universe keeps a record. Nothing is truly erased. Physicists lean toward the second view.
Most believe that information is conserved, that the universe is, at its core, a system in which the past is never truly lost. But the mechanism by which a black hole preserves and releases information remains unknown. There is something quietly profound about this. We live in a universe that may be constitutionally incapable of forgetting. Every event, every configuration of matter, every moment, it persists, encoded somewhere in the structure of what comes next. Whether this offers comfort or merely wonder is a question for each person to answer for themselves. 26,000 light-years from where you are sitting, at the center of the Milky Way, there is a black hole called Sagittarius A star. Its mass is approximately 4 million times the mass of the Sun. The stars near it orbit at speeds of thousands of kilometers per second, their paths bent by a gravitational field so intense that space itself is dramatically curved for millions of kilometers in every direction. This object has been there for billions of years. It was there before the first fish swam in Earth's oceans. It was there before the Earth existed. It will be there, slowly accreting, slowly evaporating over a timescale so vast that our minds cannot hold it, long after every star in the galaxy has burned out. We orbit it. Our solar system, our sun, our Earth, our civilization, everything that has ever lived or thought or built or loved completes one orbit around this black hole every 230 million years. The dinosaurs were alive the last time our solar system was in the position it is now. This is not a reason for despair. It is a reason for a particular kind of awe, the awe that comes from understanding scale, from grasping, however briefly, the true dimensions of the universe we inhabit. We are small. We are brief. We are made of atoms that were forged in the cores of stars that lived and died before our sun was born. We are the universe observing itself. And we have built, through centuries of careful thought and careful measurement, a set of ideas precise enough to describe what happens at the edge of a black hole, at the very boundary of knowable reality. That is an extraordinary thing, perhaps the most extraordinary thing about us. Here's what I want to leave you with. A black hole is not merely a cosmic curiosity. It is a mirror. When we study what happens at its boundary, when we ask what becomes of matter and information and time as they cross the event horizon, we are forced to confront the deepest questions about the nature of reality. We discover that time is not what we thought it was, that space can end, that the two great pillars of modern physics are not entirely consistent with each other, that there are things happening in the universe that our best theories cannot yet fully describe. And we discover that we do not know everything, that the map of human understanding still has edges, that beyond those edges is not emptiness, but mystery, deep, genuine, important mystery waiting for the next generation of minds to explore it. A black hole does not merely swallow matter, it swallows certainty. It takes what we thought we knew about the universe and reveals it as a local approximation, useful, beautiful, incomplete. If you walk away from this with anything, I hope it is this. The universe is stranger than it appears, stranger, in fact, than we have yet imagined. And that strangeness is not something to fear. It is an invitation. There is more to understand. There is always more to understand. And somewhere in the curved quiet of space-time, the universe is waiting to be asked.